Welcome to White Space, what actually happened in the 4 billion years before humans. Put this on in the background, close your eyes if you want, and let the story carry you. Let's begin. 4.5 billion years. That is the distance between us and the moment our planet came into being. Most people encounter that number in a textbook and move on. But if you were to actually travel that distance in time backward, through every layer of rock, through every vanished sea, through every catastrophe and reawakening, you would arrive at a world so alien it would be unrecognizable. No mountains, no oxygen, no sound of wind in trees, just a cooling rock bombarded from above, steaming from below. That is where we are going. What you're about to hear is a journey through the full span of life on Earth, from the first microscopic traces of biology clinging to volcanic rock, all the way to the creature that is currently listening to these words. Along the way, we will pass through 5 mass extinctions. We will watch oceans drain and refill. We will see the atmosphere itself change, not once, but several times, with consequences that reset the entire history of life each time. We will encounter monsters, some familiar, some that science has only recently given names to. And we will end where all of this has been heading, with a species that for the first time in 4 billion years has the capacity to look back and understand what happened. Let us begin at the beginning. The real beginning. The Archean Eon opened approximately 4 billion years ago and lasted for around 1.5 billion years. The planet at that time was fresh from its formation, and by fresh we mean geologically young, not remotely pleasant. In the period just before the Archean, the inner solar system was undergoing a phase of intense collisions. Asteroids and rocky bodies, the remnants of planetary formation, were striking the young Earth with enormous force. The crust that had begun to solidify over the cooling magma was repeatedly shattered and remelted. Only after this bombardment tapered off could the surface begin to stabilize. The early Earth had a face nothing like the one we know. There were no tectonic plates in the modern sense. Those vast mobile slabs of rock that collide to form mountain ranges had not yet differentiated from the upper mantle. The crust was thin, relatively uniform, composed almost entirely of basalt, which is simply solidified lava. There were no granite continents, no deep sedimentary basins, no mineral diversity of any kind. The planet was geologically monotonous. The atmosphere was equally foreign. Oxygen was essentially absent. What filled the sky instead was a dense, hot mixture dominated by water vapor, carbon dioxide and methane, along with sulfur and phosphorus compounds. The sun in this period was measurably dimmer than it is today. Some estimates put its output at roughly 30% lower. This might suggest a cold world, but the thick greenhouse atmosphere compensated, trapping what heat there was and preventing it from escaping. The result was a warm, murky, chemically active surface environment. The moon was closer, considerably closer. Its gravitational pull generated tides that would be almost incomprehensible by modern standards. Tidal waves reaching heights of hundreds of meters, sweeping across coastal zones. The day itself was shorter, rotating once roughly every 10 hours. The sky, had anything been there to look at it, would have been a dense orange-brown haze. As the planet cooled, the water vapor in the atmosphere began to condense. Rains fell, not drizzle, but sustained torrential downpours that persisted for millions of years. Water accumulated in low-lying areas, forming the first shallow seas. These primordial waters were hot, highly acidic, saturated with dissolved minerals. In some shallow pools, temperatures approached boiling. A geochemist would recognize the composition as similar to the fluid expelled by modern hydrothermal vents. And here, in conditions that would kill anything alive today, something remarkable happened. It is not entirely clear how it happened. The origin of life is one of the most actively debated problems in all of science. But what the fossil record confirms is that by roughly 3.5 billion years ago, something was alive on Earth. Not visible to the eye, not complex, but alive in the meaningful sense, self-replicating, metabolizing, responding to its environment. These first organisms were anaerobic. Oxygen was not only absent from the atmosphere, it was toxic to them. Instead, they extracted energy from chemical gradients, reactions between sulfur compounds and iron, between hydrogen and carbon dioxide, between molecules that had accumulated in the warm, reactive waters. Some of these organisms clustered around submarine hydrothermal vents, where chemical energy was continuously supplied by the geology of the planet itself. They did not need sunlight, they did not need oxygen, they required only chemistry. Archean organisms could not swim freely, they needed a surface to attach to a substrate. The biosphere of this era was therefore not a cloud of microscopic creatures drifting through open water. It was more like a thin film, a microbial coating, sometimes less than a millimeter thick, spread across the seafloor in shallow coastal zones. The dense atmosphere above blocked ultraviolet radiation, but it also limited light penetration into the water. Photosynthesis, at least the oxygen-producing kind, did not yet exist. Life was confined to the margins. The most visible trace these organisms left for us to find is the stromatolite. A stromatolite is not a creature but a structure, layered mounds of limestone built up over time by the activity of microbial communities. They trapped sediment, secreted minerals, and built up column by column into structures that could reach several meters in height. Today, living stromatolites still exist in a few places, hypersaline bays, where most other organisms cannot compete. In the Archean, they were the only life visible at any scale larger than a microscope. There was another constraint on early life. Chemistry was slow to recycle. No organism had evolved yet to break down dead organic matter. When a microbial cell died, it simply sank. It accumulated in seafloor depressions, layer upon layer, century after century. The chemical energy locked inside those cells was not returned to circulation. Over hundreds of millions of years, those organic accumulations were buried, compressed, and transformed by geological processes into the hydrocarbon deposits we mine today as petroleum. Around 3.5 billion years ago, a new ability emerged in certain bacterial lineages: photosynthesis, not the oxygen-producing kind at first, but a process that used sunlight to drive the assembly of organic molecules. It was a revolution in energy acquisition. Sunlight, after all, falls everywhere. An organism that could use it was no longer confined to hydrothermal vents or chemical hotspots. It could spread wherever there was water and light. But some lineages went further. They developed a variant of photosynthesis that used water as an electron donor and released oxygen as a waste product. This was the development that would eventually transform the planet entirely. For roughly 1 billion years, however, the oxygen produced by these organisms simply oxidized available minerals. Iron in the seawater absorbed it, turning the ancient ocean floors into bands of iron oxide. The banded iron formations that miners still quarry today for steel production. For 1 billion years, the ocean acted as a chemical buffer, absorbing oxygen before it could accumulate in the atmosphere. Then the buffer ran out. Approximately 2.4 billion years ago, the iron in the shallow seas was largely oxidized. Oxygen began to escape into the atmosphere in quantities that could no longer be absorbed. For most of the life on Earth at the time, this was not progress, it was a catastrophe. The organisms that had built the biosphere of the Archean, the anaerobic bacteria and archaea that had spent 1 billion years diversifying, were suddenly living in an atmosphere that was poisonous to them. This event, known variously as the Great Oxidation Event, the Oxygen Catastrophe, or the Oxygen Crisis, was the most complete extinction in the history of the planet. We cannot fully measure its scale. The organisms that died left almost no fossil record. We know they were extraordinarily diverse, the product of 1 billion years of evolution. We know that what replaced them was fundamentally different. The anaerobic world effectively ended. The oxygen-breathing world began. The transition was not instantaneous. It unfolded over millions of years, but its outcome was irreversible. The chemical consequences extended beyond the biosphere. The ancient atmosphere had been rich in methane, a powerful greenhouse gas. As oxygen accumulated, methane oxidized into carbon dioxide and water. Carbon dioxide is a weaker greenhouse gas. The warming effect of the atmosphere dropped. Temperatures on the planetary surface fell. The result was the most extensive glaciation in Earth's history. The Huronian glaciation, which began approximately 2.4 billion years ago, lasted for around 300 million years. Geological evidence suggests that ice sheets spread as far as equatorial latitudes. The planet came close, perhaps came very close to what some researchers call a snowball Earth event, in which ice covered the entire surface from pole to pole, reflecting so much sunlight back into space that warming became nearly impossible. In 1.5 billion years, the Earth had gone from a world of boiling lava fields and acid seas to a frozen globe locked in ice. Life persisted. It always persisted. But it was confined, reduced, slowed nearly to a halt. The Proterozoic eon, which extended from 2.5 billion years to roughly 542 million years ago, was in many respects a waiting period. Single-celled life continued its slow evolution, oxygen levels gradually rose further. Eventually, around 1.5 to 2 billion years ago, the first eukaryotic cells appeared, cells with a true nucleus, capable of much greater complexity than anything that had come before. These were the ancestors of every plant, animal, and fungus that would ever live on Earth. Land throughout this entire period remained empty, not just uninhabited by animals, uninhabited by anything visible. The continents were bare rock, swept by wind and rain. Without roots to hold soil in place, erosion moved freely. Without organic matter to build soil structure, the ground was sterile. The oceans, meanwhile, continued their slow evolutionary work in coastal zones, particularly near the equator where sunlight was strongest. For most of the Proterozoic, if you had stood anywhere on dry land and looked around, you would have seen nothing living at all. The last period of the Proterozoic, known as the Ediacaran, began approximately 635 million years ago. The Earth was finally warming again after another major glaciation. Oxygen concentrations in the atmosphere, though still only a fraction of today's levels, were rising toward a threshold that would allow larger, more complex organisms to sustain themselves. And in the coastal waters of the late Ediacaran, something new had appeared. These organisms were unlike anything before or after them. Soft-bodied, many of them immobile or nearly so, they did not resemble any modern animal in any obvious way. Some were flat, like quilts lying on the seafloor. Others were radially symmetric, branching like fern fronds. They appeared to have had no mouths, no digestive systems as we would understand them, no hard structures. They absorbed nutrients directly from the water or from organic films on the seafloor. For roughly 40 million years, these creatures, the Ediacaran fauna, were the dominant large life forms on the planet. Then they disappeared. Not gradually, but relatively quickly by geological standards. And what replaced them was more familiar and far more dangerous. Approximately 542 million years ago, a transition occurred in the fossil record so dramatic that geologists use it to mark the boundary between the Proterozoic and the Phanerozoic. Below this boundary, fossils are sparse and strange. Above it, the rock is suddenly filled with complex, hard-bodied creatures of enormous variety. This is the Cambrian explosion, and the word explosion, though dramatic, is not quite right. It unfolded over several million years, but by geological timescales that is extraordinarily rapid. What drove it? The leading hypothesis involves predation. Near the end of the Ediacaran, the first predators evolved organisms capable of actively pursuing and consuming other living things. Before this, life on the seafloor was a largely passive affair. Afterward, it was an arms race. Prey needed ways to defend themselves: shells, spines, speed, the ability to burrow. Predators needed ways to breach those defenses: stronger jaws, better sensory systems, greater speed. Each adaptation in defense drove an adaptation in offense. The evolutionary feedback loop accelerated everything. The Cambrian seas teemed with life. Trilobites, armored arthropods with segmented bodies and compound eyes, became so abundant and widespread that their fossils are found on every continent. Anomalocaris, reaching up to 60 centimeters in length, was among the apex predators. A creature with articulated grasping appendages near its mouth, large compound eyes, and a swimming body that moved by rippling fin-like lobes along its sides. It had no close relatives among any modern animal group. More significant for the long arc of life on Earth were the chordates, creatures that possessed a flexible internal rod running along their length, the forerunner of the vertebral column. Some of these early chordates were small bottom dwellers resembling modern lancelets. Others were slightly larger and more active. Around 530 million years ago, tiny creatures such as Haikuela developed features that placed them among the earliest known relatives of vertebrates. A little later, Pikaia appeared, a swimming, worm-like creature that propelled itself through S-shaped body undulations, using the efficiency of a flexible internal support structure rather than an external shell. These were not impressive animals by any measure. They were small, soft, and probably slow, but they carried a body plan that would eventually produce fish, amphibians, reptiles, birds, and mammals. Meanwhile, on land, the first tentative colonization was occurring. Fossil soils dating to around 530 million years ago contain microscopic traces of early algae and primitive microorganisms. These were not plants as we would recognize them. They had no stems, no leaves, no root systems, but they could photosynthesize, they could grow on moist rock surfaces. They died, decomposed, and left behind a thin organic residue. Slowly, over millions of years, this residue built up into something resembling a primitive soil. Fungi followed. Single-celled algae and primitive fungi formed partnerships, the symbiosis that eventually, roughly 100 million years later, produced lichens. Lichens can colonize bare rock. They survived desiccation, extreme temperature swings, and ultraviolet radiation and remain the pioneer organisms of newly exposed or barren surfaces. In the early Paleozoic, they were the vanguard of the entire terrestrial invasion. The Ordovician period, which followed the Cambrian, lasted from approximately 485 to 443 million years ago. In the seas, life continued to diversify. Mollusks proliferated. Arthropods called eurycterids, sea scorpions, were among the dominant predators in many habitats. Jawless fish, ancestral to lampreys and hagfish, patrolled the shallow coastal waters. Cartilaginous fish appeared later in the period. The marine ecosystem was becoming genuinely complex, with multiple trophic levels: grazers, filter feeders, predators, scavengers, all interacting. On land, the process was slow. The first multicellular plants capable of surviving outside water appeared, leaving behind fossilized spores and fragments of vascular tissue. They had no true roots, no woody structure, no capacity to grow tall. They clung to wet margins, riverbanks, tidal zones, the edges of estuaries. The Ordovician ended badly. An extinction event of significant scale eliminated somewhere between 40 and 60% of marine genera. The most widely accepted explanation involves a rapid glaciation centered on the southern supercontinent Gondwana, which occupied the pole at the time. Sea levels dropped as water became locked in ice. Shallow marine habitats which hosted the greatest biodiversity were drained or drastically reduced. When the ice melted and sea levels rose again, the disruption killed additional species. It was a two-phase disaster. Life recovered. It always recovered. The Silurian period, spanning from 443 to 419 million years ago, saw a rebound. Coral reefs expanded, fish diversified. The eurypterids reached extraordinary sizes. Some specimens exceeded 2 meters, and the largest known Echolopterus approached 3. The ocean was a genuinely dangerous place. On land, the first vascular plants with internal plumbing capable of moving water upward against gravity, appeared near water sources in tropical zones. These early colonizers were still small, rootless, and confined to consistently wet areas. But their presence created the first terrestrial food base for animals. The pressure to escape predation, combined with the pull of an untapped food supply, drove the first arthropods onto land. Eurypterids and other crustaceans were pre-adapted for the transition in ways that fish were not. Their exoskeleton provided structural support outside water, resisted desiccation to a degree, and contained the body against the flattening force of gravity. Their jointed limbs evolved for locomotion in water, translated reasonably well to movement on solid surfaces. The first terrestrial arthropods stayed close to the water's edge, and their respiratory structures needed to remain moist to function. But the food was there, the predators were not, and the transition had begun. The Devonian period, running from 419 to 358 million years ago, is often called the Age of Fishes. And for the sea, this is accurate, but the more important story of the Devonian happened at the water's edge. By this point, plants with genuine vascular systems had spread inland from the coasts. Rhiniophytes, the earliest representatives of this group, were simple forking stems without leaves, reaching about a meter in height. Later, more complex lineages developed, ancestors of ferns, horsetails, and eventually seed plants. In warm, wet zones, forests of a kind were taking shape, but these forests had a problem. The trees, if we can call them that, had not yet evolved deep root systems instead of true roots that penetrate and anchor soil. They had shallow rhizomes, horizontal stems that lay along the surface. Without deep roots, soil had nothing to hold it against rainfall. Rivers ran thick with eroded sediment. Lowland areas became waterlogged. Swamps spread across deltaic and coastal environments. These swamps were ecologically rich. Insects and their larvae thrived in the warm, organic, saturated water. Fish followed the food in the swamps. However, conditions presented a new problem for fish: periodic oxygen depletion. The decomposition of enormous quantities of organic matter consumed dissolved oxygen. During certain seasons or weather events, oxygen levels in the water dropped to near zero. Some fish responded by evolving the ability to breathe atmospheric air. The capacity to gulp air from the surface using a rudimentary lung-like organ allowed fish to survive these episodes. But air breathing created another opportunity. If a fish could breathe air, it could potentially leave the water entirely, at least temporarily. To do that, it needed something other than fins. The fossil record of the late Devonian documents this transition in remarkable detail. Eusthenopteron and related sarcopterygian fish, lobe-finned fish, whose fins contained internal bone structures analogous to the limb bones of tetrapods, used their muscular fins to move through dense aquatic vegetation. When swamps dried out, some individuals crawled across dry land to reach the next pool of water. Those whose fins were stronger and whose lung function was better survived the crossing. Over millions of generations, natural selection shaped fins into limbs. Acanthostega, which lived approximately 365 million years ago, represents an extraordinary transitional form. It had 4 recognizable limbs. It had a wrist joint. Its head was distinctly non-fish-like in its proportions. But it also had gills, retained a fish-like tail fin, and its limbs were not strong enough to fully support its weight on land. It almost certainly spent most of its life in shallow water. The limbs may initially have been more useful for maneuvering through underwater vegetation than for walking on land. Tiktaalik, another late Devonian transitional form, carried the adaptation further. Its pectoral fins had a shoulder, elbow, and wrist, the 3-segment limb structure inherited by every land vertebrate that followed. It could do something no fish before it could do: push itself up off the substrate. Its neck was mobile, allowing it to turn its head without turning its entire body. Its sensory organs were adapted for both aquatic and terrestrial environments. Tiktaalik was not yet committed to land, but it was equipped for it. The Devonian ended with another major extinction, this one affecting primarily marine ecosystems. As land plants expanded inland and developed deeper root systems, they extracted minerals from soil and rock at unprecedented rates. Rain washed these nutrients into rivers and eventually into coastal seas. The nutrient influx triggered massive algal blooms. When those algal masses died and sank, their decomposition consumed oxygen dissolved in the water column. Dead zones spread across seafloor habitats. An estimated 70% of marine species were lost, including virtually all the organisms that had built the reef ecosystems of the early Paleozoic. The Carboniferous period, which followed from 358 to 299 million years ago, was a world of forests. The descendants of those early vascular plants had by now evolved into genuine trees, woody-stemmed, tall, capable of forming dense canopy. In the tropical zone, coal swamp forests of Lepidodendron and Sigillaria reached 30 to 40 meters in height. Their bark was sculpted in geometric patterns. Their root systems were shallow but broad. There was, however, a critical gap in the ecology of these forests. Nothing had evolved to digest wood. Lignin, the tough structural polymer that gives wood its strength, is chemically resistant and biologically difficult to break down. No organism alive in the early Carboniferous had the enzymatic toolkit to decompose it efficiently. When trees died, they fell and lay intact. Layer upon layer of dead wood accumulated across the forest floor, preserved by the waterlogged conditions of the swamp environment. Over millions of years, these accumulations were buried under sediment, compressed, and cooked by geological heat into the coal deposits that would later fuel the Industrial Revolution. The oxygen content of the atmosphere during the Carboniferous reached levels far above those of today. Estimates range up to 35%, compared to roughly 21% now. Fires burned more readily, but more consequentially for biology, insects grew to extraordinary sizes. High oxygen concentrations allowed passive diffusion of air through the tracheal systems of arthropods to sustain much larger bodies. Arthropleura, a giant millipede, reached 2.5 meters in length. Meganeura, an ancestor of dragonflies, flew with a wingspan approaching 1 meter. Pulmonoscorpius, a scorpion, measured 70 centimeters. The first reptiles evolved in the Carboniferous. Their key innovation over amphibians was the amniotic egg, an egg that could be laid on land, enclosing the embryo in a self-contained aquatic environment within a protective membrane and shell. Freed from the need to return to water to reproduce, reptiles could colonize fully terrestrial environments. The vertebrate invasion of land had found its final key. The Permian period, from 299 to 252 million years ago, saw the continued diversification of both reptiles and a group known as synapsids, creatures often described as mammal-like reptiles, though the relationship is more direct than that description implies. Synapsids were not reptiles that became mammals. They were a distinct lineage whose Permian representatives were diverse and widespread. Among them were the dicenodonts, medium to large herbivores with two prominent tusks, and the therapsids, whose descendants would eventually become the first true mammals. The Permian ended with the most catastrophic event in the history of multicellular life. The Permian-Triassic extinction, sometimes called the Great Dying, occurred approximately 252 million years ago. By the best available estimates, up to 95% of marine species and 70% of terrestrial species were eliminated. The biosphere was reduced to a fraction of its Permian diversity. The cause or causes remain partially unresolved. The most significant factor was almost certainly massive volcanic activity. The eruption of the Siberian Traps, one of the largest known volcanic provinces in Earth's history, which released enormous quantities of carbon dioxide and sulfur dioxide over a geologically brief period. Global temperatures spiked, ocean chemistry shifted, anoxic conditions spread through the water column. Whatever the precise mechanism, the recovery was slow. It took tens of millions of years for species richness to return to pre-extinction levels. Life had survived, but barely. The Triassic period opened 252 million years ago into a world emptied by disaster. The supercontinent Pangaea was still largely intact, stretching from pole to pole, creating the conditions for extreme continental climates, hot, dry, with pronounced seasonal variation. Much of the interior was desert. The ecological niches left vacant by the extinction were in time filled, but by different groups than had occupied them before. The archosaurs emerged in the Triassic as one of the most important vertebrate lineages of all time. From this group descended three major lineages still represented today: the crocodilians, which have changed relatively little since the Triassic; the pterosaurs, which evolved powered flight and dominated the Triassic and Jurassic skies; and the dinosaurs, which would come to define the second half of the Mesozoic era. The early dinosaurs were not the giants of popular imagination. In the early and middle Triassic, they were small to medium-sized predators, competing with a variety of other archosaurs for ecological space. It was only toward the end of the Triassic, coinciding with a sudden rise in atmospheric oxygen, that dinosaur body sizes increased sharply. By the time the Triassic-Jurassic extinction event swept away many of their competitors, approximately 201 million years ago, the stage was set. Alongside the archosaurs, the synapsid lineage was quietly producing its own revolution. Lystrosaurus, a dicenodont synapsid, survived the Permian-Triassic extinction in enormous numbers and dominated early Triassic ecosystems before being displaced by the expanding archosaurs. More interesting in some respects is a creature like Adelobasileus or its close relatives in the late Triassic, small, probably warm-blooded, possibly fur-bearing animals that represent the transition toward true mammals. One such creature, Morganocodon, lived in the late Triassic, approximately 200 million years ago. It was roughly mouse-sized, with a thin, flexible body teeth that were replaced only once during its lifetime, a mammalian characteristic, and a jaw structure that was transitional between the multiple-boned reptilian jaw and the single-boned mammalian one. These creatures were small, probably nocturnal, and lived under the feet of the large Triassic archosaurs. That smallness likely saved them. The Jurassic period began 201 million years ago after the Triassic-Jurassic extinction event. Pangaea was now actively breaking apart. A rift was widening between what would become North America and Africa. The Tethys Sea separated the northern and southern land masses. These divisions had direct evolutionary consequences. Populations of organisms on different land masses were isolated from one another and began diverging. The Jurassic climate was warmer and more humid than the Triassic had been. Forests spread to higher latitudes, cycads and conifers dominated the landscape. the diversity of ecosystems expanded. And into these ecosystems went the dinosaurs in a proliferation of forms that is difficult to fully comprehend. Sauropods, the long-necked, long-tailed herbivores, evolved to enormous sizes. Brachiosaurus, whose front legs were taller than its hind legs, giving it an upright giraffe-like posture, stood perhaps 12 meters at the shoulder. Diplodocus reached 27 meters in length, though most of that was neck and tail. The largest of the group, Argentinosaurus and related titanosaurs, may have reached 30 to 35 meters and weighed 70 to 80 tons. These were the heaviest animals ever to walk on land. The sauropod body plan posed an interesting neurological puzzle. The spinal canal in some sauropods widened dramatically in the sacral region, creating a space far larger than the cranial cavity. For many years, this was interpreted as a second brain, a rear control center for the hindquarters. Current understanding suggests the cavity was more likely filled with glycogen, a stored energy source for the nervous tissue of the spinal cord. The primary brain was relatively small. These were not intellectually sophisticated animals. In the seas, the dominant predators of the Jurassic were marine reptiles. Ichthyosaurs, which had evolved from terrestrial reptile ancestors that returned to the sea during the Triassic, reached their peak diversity and ecological importance in the Jurassic. The transition from their Triassic ancestors to their Jurassic forms is a striking illustration of convergent evolution. Their bodies converged toward the streamlined, fish-like shape optimized for aquatic locomotion, independently arriving at many of the same solutions that fish had evolved hundreds of millions of years earlier. Ophthalmosaurus, a Jurassic ichthyosaur, had eyes of extraordinary size, up to 10 centimeters in diameter, protected by a bony ring. It was adapted for deep water, low-light hunting, able to dive to depths exceeding 600 meters and remain submerged for up to 20 minutes. Also in the Jurassic, the first true birds appeared. Archaeopteryx, the most famous early bird, retained many features of its dinosaurian ancestors: teeth, clawed wings, a long bony tail, while already possessing true feathers. The boundary between birds and feathered dinosaurs is now understood to be gradual rather than sharp. Many non-avian dinosaurs possessed feathers, and the transition to powered flight involved incremental changes in anatomy that accumulated over millions of years. The Cretaceous period, which began 145 million years ago and lasted approximately 79 million years, was in many respects the culmination of the Mesozoic world. The continents had by now taken on shapes close to their modern configurations, though positioned differently. India was an island drifting north across the Tethys. South America was separating from Africa. The Atlantic Ocean was widening. One of the most consequential biological events of the Cretaceous was the rise of flowering plants. Angiosperms first appeared in the fossil record in the early Cretaceous and diversified rapidly, spreading from tropical latitudes outward. They developed intimate relationships with insects, using flowers to attract pollinators and fruits to disperse seeds. This co-evolutionary relationship drove diversification in both groups. By the late Cretaceous, grasses had appeared. Grass is biologically unremarkable in some ways. A plant without showy flowers, without dramatic adaptations, but grass forms dense mats. Its fine roots stabilize soil at a level that earlier plants could not match. Grasslands replaced open habitats that had previously been either sparse vegetation or bare ground. New ecological structures, new food chains, new habitats came into being. Among the mammals of the Cretaceous, Repenomamus stands out as an exception to the general rule of small, nocturnal mammalian life. This creature, found in early Cretaceous deposits of what is now China, measured up to a meter in length and weighed 12 to 14 kilograms. a fossilized specimen was found with the partial remains of a young dinosaur in its stomach, direct physical evidence that some Cretaceous mammals actively preyed on small dinosaurs. In the Arctic regions of the late Cretaceous, approximately 70 million years ago, an unusual tyrannosaur lived in the permanent twilight of polar winters. Nanooksaurus, whose name means polar bear lizard in the Inupiaq language, was a scaled-down relative of Tyrannosaurus rex, reaching perhaps 6 meters in length and 1,000 kilograms, roughly 1/10 the mass of its larger southern relatives. The reduction in size appears to have been an adaptation to a leaner food supply in the high-latitude environment. Its skull structure, preserved in fossil fragments, suggests enlarged olfactory regions and unusually large optic lobes, sensory adaptations for hunting in darkness. It was likely warm-blooded in the modern avian sense, with feathering to preserve body heat. It probably brooded its eggs and engaged in extended parental care. Nanooksaurus is a useful reminder that even the most familiar categories of dinosaur, the fearsome theropod predator, were far more ecologically and physiologically diverse than popular culture typically acknowledges. About 66 million years ago, all of it ended. The Cretaceous-Paleogene extinction event removed all non-avian dinosaurs from the planet, along with the flying pterosaurs, the large marine reptiles, and a substantial fraction of every other group. The cause most widely accepted is the impact of an asteroid approximately 10 to 15 kilometers in diameter at the site, now known as the Chicxulub crater in the Gulf of Mexico. The immediate effects, a global firestorm, a years-long impact winter caused by debris blocking sunlight, were catastrophic. Secondary effects, including acid rain, a prolonged collapse of photosynthesis, and food chain disruption from the bottom up, extended the damage over decades and centuries. Approximately 3/4 of all living species were eliminated. What remained were small-bodied animals that could survive on minimal food, tolerate temperature extremes, and exploit a wide range of food sources. Among these survivors were the mammals. The Cenozoic era opened into a world stripped of its dominant fauna and flora. For the first 10 million years, the Paleocene epoch, the Earth was recovering. The process was not simply a filling in of vacant ecological slots by whatever creatures happened to survive. It was a genuine restructuring, new body plans, new ecological relationships, new evolutionary trajectories starting from different ancestral points than those that had prevailed before. In this recovering world, mammals radiated with remarkable speed. The carnivorous mammals, which would eventually produce all the large predators familiar today, descended from the Miacids, small, agile, weasel-like creatures of the early Paleocene. The lineage leading to whales and dolphins began with terrestrial animals in the Paleocene and Eocene that appear more related to hippos and pigs than to any modern aquatic mammal. Pachycetus, an early member of the whale lineage, was a four-legged terrestrial animal that probably spent time in water, much as modern hippos do. Its descendants would, over the course of roughly 15 million years, lose their hind limbs, flatten their forelimbs into flippers, develop a horizontal tail fluke, and move their nostrils to the top of their head. The Eocene epoch, spanning from 56 to 34 million years ago, was the warmest period of the Cenozoic tropical forests extended to unusually high latitudes. Diversity was high, and among the carnivores of the time was one of the largest mammalian predators ever to have lived, Andrewsarchus, known primarily from a single enormous skull measuring 84 centimeters. Belonged to a group of primitive ungulates, more closely related to hippos and even to whales than to any modern predator. Its reconstructed body may have reached 4 meters in length and weighed close to a ton. The paradox of a hippo relative that was the dominant apex predator of its time is a useful illustration of how different the Eocene world was from our own. The Oligocene epoch, which followed from 34 to 23 million years ago, brought a significant cooling. Tropical forests retreated, grasslands expanded. The Antarctic ice sheet began to form, permanently reshaping global ocean circulation and climate. In the open grasslands of this cooler world, new types of large herbivores evolved to exploit the grass-dominated habitats. Among the largest was Paraceratherium, a relative of modern rhinoceroses, but built on a completely different scale. Standing nearly 5 meters at the shoulder and capable of raising its head to roughly 7 meters above the ground, it was the largest land mammal known to science. Its mass reached an estimated 15 to 20 tons. A modern elephant would stand comfortably under its belly. A modern rhinoceros would pass under its chest. These animals moved in small groups across the open woodlands and early grasslands of Eurasia, browsing the high canopy. Paraceratherium had no natural predators at its adult size, but the Oligocene also produced Entelodon, sometimes called the hell pig, though it was more closely related to hippos, a heavily built omnivore reaching 1.8 meters at the shoulder, with a skull adapted for crushing bone and a behavioral ecology that probably included active predation, scavenging, and aggressive territorial behavior. Fossil sites preserve entelodont bone beds alongside the remains of horses and other large herbivores, with unmistakable bite marks. The Neogene period, from 23 million to approximately 2.6 million years ago, brought the continents essentially to their modern positions. The Mediterranean basin, long partially isolated from the global ocean, periodically dried and refilled. North and South America were separated by ocean until approximately 3 million years ago, when the Isthmus of Panama formed and the Great American Biotic Interchange began. Animals that had evolved in isolation for tens of millions of years suddenly found themselves sharing continents. The consequences were severe for many South American species, whose ecological roles were taken over by the more recently diversified North American fauna. In the Neogene seas, Megalodon, a shark estimated at 15 to 18 meters in length and up to 50 tons, was the apex predator. Its teeth, which are the primary fossil evidence for the species, reach 17 centimeters in length. By comparison, the largest tooth of a great white shark rarely exceeds 7 centimeters. What Megalodon actually looked like beyond the teeth remains debated, since sharks leave little skeletal material other than teeth and a few other calcified structures. On land, the elephants and their relatives, the proboscideans, were diversifying into a remarkable array of forms. Many carried 4 tusks rather than 2. Some had tusks that curved sharply downward, adapted for digging. Others had flattened lower tusks used for scraping bark or excavating soil. The diversity of the group in the Neogene far exceeded the 3 living proboscidean species we have today. The Quaternary period, which began approximately 2.6 million years ago and continues to the present, was characterized by cycles of glaciation, the ice ages. Ice sheets advanced and retreated across the northern hemisphere on roughly 100,000-year cycles, reshaping coastlines, redirecting rivers, and fragmenting habitats. The cold and warm phases drove rapid evolutionary change in many lineages, including our own. Gigantopithecus, the largest known primate, lived in Asia from roughly 2 million to 300,000 years ago. Standing an estimated 3 to 4 meters tall and weighing over 500 kilograms, it was related to modern orangutans. Its size paradoxically limited its options, too heavy to climb trees as its relatives did. It was forced to remain on the ground. Evidence from fossilized teeth suggests it was primarily herbivorous, likely consuming bamboo and other plant material. Dental wear patterns indicate a diet not unlike the modern giant panda. Whether it used tools, built shelters, or had any social complexity beyond what its brain size implies is unknown. Diprotodon, which inhabited Australia from 1.6 million to roughly 40,000 years ago, was the largest marsupial that ever lived. Reaching 3 meters in length and close to 3 tons in weight, it was related to modern wombats and koalas, but scaled to a size more comparable to a hippopotamus. It was herbivorous, and it moved in herds across the woodland and grassland environments that covered Australia before the arrival of humans. Humans arrived in Australia approximately 50,000 years ago. Within a relatively short period, the precise timing is still debated. Diprotodon and most other large Australian mammals were gone. Whether the primary driver was hunting, habitat change through the use of fire, or environmental shifts unrelated to human presence remains contested. The coincidence is difficult to argue away. The same pattern repeats across the globe. Megafauna extinctions cluster geographically and temporally with the spread of Homo sapiens across previously uninhabited continents. The Holocene epoch, which began approximately 11,700 years ago at the end of the last major glacial period, is the epoch in which all of recorded human history has occurred. In geological terms, it is an eye blink. In biological terms, it has been a continuation and acceleration of the trend that began with the first human migrations out of Africa, a progressive simplification of the biosphere with diverse ecosystems replaced by human-managed landscapes and the species that can survive alongside human activity. The paleontological record of the past 540 million years shows 5 episodes that qualify as mass extinctions by the technical definition, events in which more than 75% of species disappeared over a geologically brief interval. Some researchers now argue that we are in the early stages of a sixth. The current extinction rate is estimated at 100 to 1,000 times the background rate observed in the fossil record. Amphibians, reef-forming corals, and large mammals are among the most severely affected groups. The primary drivers, habitat destruction, overhunting, invasive species, ocean acidification, and climate change, are all products of human activity. This is the first extinction event in the history of life on Earth that is being driven by a biological agent from within one species. Through the ordinary exercise of its capacities, building, farming, traveling, burning is altering the conditions of life for every other species on the planet. Whether that constitutes an indictment of our species or simply an observation about the power of intelligence applied at scale is a question for a different kind of documentary. What the fossil record tells us, unambiguously across billions of years, is that life on Earth does not end. It has survived the freezing of the oceans, the poisoning of the atmosphere, the impact of asteroids, and the drowning of continents. After every extinction, whatever remains diversifies into the vacant space. The forms that emerge are not predictable from what came before. The Triassic world could not have predicted the Jurassic. The Cretaceous world could not have imagined the Cenozoic. Whatever follows us will be equally unforeseeable. The history of life is not a story with a destination. It is a story about capacity, about the seemingly endless ability of matter organized in just the right way to persist, adapt, and find new configurations in the face of whatever the universe provides. We are one of those configurations. We have been here for a remarkably short time. The question of how long we remain is one that only we can answer. The rock